With the Leica Absolute Tracker, hexagon metrology introduces a cutting-edge solution to an age-old problem. The Absolute Interferometer, or AIFM, offers the ability to measure absolute distances with the highest precision, whilst at the same time being able to instantly re-establish a broken laser beam and immediately start measuring a moving target. Let us explain to you how we have combined the best capabilities of laser interferometers and absolute distance meters to achieve this major breakthrough. In the ideal world, a laser tracker would measure absolute distances with the highest precision and would be arbitrarily fast with near zero integration times, the time required to determine the target's position. Until now, no single distancing unit was capable of this. As a result, laser tracker manufacturers were forced to use both laser interferometers and absolute distance meters, or ADMs, separately. Each individual technology has its own strengths and weaknesses. A laser interferometer, or IFM, can determine relative distances, i.e. the change in distance from point to point, with accuracies on the nanometer level. However, change in distance, or relative motion, is all that they are capable of measuring. A laser beam is projected from the system to a reflector with both the exiting and returning beams being monitored. As the reflector is moved, the return beam moves and the wave peaks cross each other, creating a superposition wave. Every time this superposition wave peaks, it represents a change in distance of half of the wavelength, or in the case of the AIFM, 0.32 microns. Not only is this incredibly accurate, but it is also almost instantaneous. The update rate is given only by the speed at which the reflector can be moved. This makes laser interferometers perfect for dynamic measurements, because no matter how quickly the target accelerates, the exact change in location is immediately known. They have been an industry standard for over 30 years and remain the most accurate system for measuring large distances available. An ADM, on the other hand, measures absolute distances, or distances to a known point in a 3D coordinate system with extreme precision. But even the fastest ADM will never be able to achieve the speed of an IFM for dynamic measurements. All absolute distance meters must deal with integration times. This is the time required to perform the operations that determine the target's position. In order for our polarization modulation principle to calculate a distance accurately, we need to analyze the return waveform for a period of time to determine the minimum point, or the lowest point, of the wave. This measurement of the wave is a type of wobble measurement, which jumps back and forth over the lowest point of the wave to create a measured mean value. Once the minimum point is measured, then the absolute distance can be calculated. With our previous technology, the reflector had to remain stable during this wobble measurement. If the reflector moved, then the waveform moved, and thus the minimum point and calculated distance changed as well. A phenomenon that we were never able to take full advantage of with our previous ADM design was that even if the reflector was moving, the waveform wouldn't change shape. It would just move relative to the distance that the reflector had moved. This meant the reflector didn't need to be stable during integration. We just needed to be able to monitor its relative movement. The AIFM combines the absolute measurement from the ADM with the interferometer to create the absolute interferometer. As soon as a reflector is brought into the laser beam or locked on, the IFM starts tracking its relative movement. Even if the reflector is moving at the maximum speed and acceleration allowed by the laser tracker, the IFM can still deliver sub-micron positional information to the ADM. The ADM then measures the wave as described previously, but uses the information from the IFM to compensate for the movement. As soon as the minimum point is calculated, the absolute distance is fed back to the IFM, changing it from a relative interferometer into an interferometer with absolute reference, or what we call the absolute interferometer. The AIFM combines the best of both worlds. It provides a leading-edge solution to an age-old problem, but does so using mature technology. The IFM and ADM core technologies have been used for more than a decade in our laser trackers around the world. These core technologies have been improved and combined to create what we have dubbed the Absolute Interferometer, or AIFM, and represents the most accurate and stable dynamic distancing unit that we have ever created.